Thank you very much sincerely to Nick and Chris for inviting me here, to the organizing committee for putting on a wonderful show, and for all the people who helped put this together. As you can see, I'm bifurcated between two institutions. I'm still finishing my PhD from U of T, but for the last few years we have lived in the extreme northwestern corner of Canada, an hour and a half drive away from Alaska, and I am now in my second year of teaching more or less full-time at Yukon College. So between the two places, and both helped me to be here, so I'm grateful to them for that. So here's one slide about Yukon College. It's the only post-secondary institution in the Yukon. It has 13 community campuses across the territory. Some of these communities have 300 to 500 people, so it's quite impressive, its reach. And it tries to be a one-size-fits-all approach. So we teach everything from the trades, like mining, to first-year sciences and liberal arts. So unfortunately, I don't teach in the trades. I'd love to know how to operate something like that. I don't. But I'll teach anything they throw my way. So I do the first-year physics, calculus, and ethics courses, and so far. So at one end, it has the only art school north of 60 degrees latitude in either Canada or the US here in Dawson City. So, and that's the main campus where I am. So it's a nice.
What's the logo? Is that a good?
It's a loon. Yeah. It's that ubiquitous. It's that ubiquitous sound when you're canoeing in the wilderness that I won't try to imitate it. Okay. Anyway, so the mystery that we want to try to solve today, though, is, or try to get a handle on knowing where to go, is background independence. So I'll start with a Ravelli quote, but it's not a quote about partial observables or that program. So I felt licensed to bring up another quote anyway from him. Everybody says they want background independence, and then when they see it, they're scared to death by how strange it is. Background independence is a big conceptual jump. You cannot get it for cheap with conventional means. So what am I going to try to cover and try to not cover? I'll try to square off or limit my space here. So what I will try to do is to give you my idea of teasing out different ways in which background independence is understood in classical field theories. I won't pretend that this is every possible way you could interpret theories as being background independent, but I'll give you some recipe to start to show that there's some traction in splitting up this concept, maybe to mean different things. And then I'm going to try to tease out analogs within various different quantum gravity programs about different ways to understand background independence, flowing more or less from the teasing out I do in part one. So the question there really is, in what sense does background independence carry over? In what way can we say that a certain theory is background independent or not? And is that different from the way someone else says their theory is background independent? Does it make any difference? The big question, the really interesting question, which I won't be able to answer today, I won't even pretend to tackle just because I only have the one talk, is the motivational question. Why should we care at all about background independence? So I won't try to address that in the talk at all, because I'm just trying to do a teasing out now first, so that maybe in a later stage I can talk about the motivation. It's always good, I think, to summarize, if possible, a talk on one slide. This is what I do when I teach my ethics class late in the afternoon. I jar the students every once in a while. I say, please, just if you pay attention to this one slide, if you get what's on here, you'll be fine. That's all I really wanted to talk about today. So, in this talk, I'm trying to show that the way you understand background independence is going to lead you to either appreciate the title of this book, that there is no time, or this book, that in fact time is the only thing that's real. So I won't talk about the approaches taken in either of those two popular books, but the title is what stands out for me. It's either it's the end of time or time's all there is. So here's the plan. I'll give you three views of background independence as I see them in classical GR. And I'll give you three different views of background independence in quantum gravity, or at least I'll talk about three different approaches in quantum gravity and show how they may or may not instantiate certain kinds of background independence. And then I'll give you my musings about what I think that means about time. Okay. The first way I think we can understand background independence is a fairly obvious one. It's hard to pin down a name for it though, because it goes under so many guises, but let's just call it diffeomorphism invariance for now, and I'll try to tease it out in more detail. So here's the setup. So this follows the approach in two articles, Giulini and Rickles. So we start by just giving a very generic, I won't even say which kind of, or which specific classical field theory, just some generic field theory T that's describable in this model, MDB, where M is an infinitely differentiable manifold. Working backwards to the right-hand end first, the D is going to be the dynamical fields. So those are the fields that must be solved in order to get their values, like the metric in GR, or the electromagnetic field in Maxwell's. Now, what are the possible values of these fields? So the kinematically possible values of the D fields can live in a space K of field configurations, and B represent background fields, so fields whose values are independently specified or fixed. You're not going to be solving these in the theory, you're going to be somehow starting off with them or imposing them in by hand. So I'll say later what a background field might be, but that's the way I'll split them up in the model. So define a set of differential equations, equations of motion, you can think of it that way. And so these equations will determine a space S of possible solutions to the theory. So where you would solve for your D fields, your dynamical fields, given any B fields that might be there. So your solution space obviously is going to be a subset of the kinematically possible states of the theory, because you're doing dynamics. And define a space-time symmetry group G of T of the theory, which is simply the group of all diffeomorphisms of M. So this will act on K such that kinematically possible solutions are mapped to other kinematically possible solutions, so that the solution space is itself invariant. So by individual diffeomorphisms, I'm just going to mean elements of this symmetry group G. Okay, now based off that setup, we can try to differentiate what covariance and what invariance might mean. So covariance is going to be simply where I'm going to hit both the D fields and the B fields with the diffeomorphism and see no physical change. So Giulini and Rickles define covariance in this way, general covariance in this way, as has been noted before, as a formal constraint. So when we hit a solution of the theory with an arbitrary diffeomorphism, we simply get another solution back. All fields, both dynamical and background, which are those independently fixed, are subject to the same diffeomorphism and thereby preserve the same dynamical content. Wheeler, as we all know, derides this as mere bookkeeping. Another possible definition is passive diff invariance. Invariance, on the other hand, looks like this. I'm not going to hit the background fields with the diffeomorphism. So what's going to happen? So in an invariance group there, or in the invariance relation rather, the diffeomorphisms are applied only to the dynamical fields, leaving the background fields intact. So in comparing them now, so long as the theory is well formed, the covariance group will simply represent the full group of space-time symmetries, but the largest symmetry group that satisfies the invariance is going to, of course, vary from theory to theory. So in special relativity, the largest such group will be the Poincaré group, and that's only a subgroup of the full diffeomorphism group. So in context of special relativity, the covariance group does not equal the invariance group. The supposed novelty of GR is that precisely here, uniquely among classical field theories, you do have the covariance group equaling the invariance group, and that's for the reason that's trivial in the setup, so the setup is kind of biased to show this, that the B fields are the empty set, there's no background field. So the setup is kind of meant to really easily show that. So this is well known as active diffeomorphism invariance. So the first definition of background independence from the classical point of view could be simply this, where the covariance group equals the invariance group. But the intuitive idea here, and I'm purposefully being very hand-wavy because when we're going to talk about different quantum gravity theories, it's not even clear that some of them can be considered field theories. Maybe something will emerge from them to be a field theory or to look like a field theory. I don't know, but that's why I'm purposely leaving it quite open now. I just want to get at intuitive concepts. Let's call this something like the gauge redundancy view or gauge equivalency view or multiple realizability. Basically the hand-wavy intuitive idea that we've achieved some kind of background independence if we have mathematically equivalent descriptions of the same physical reality. Okay, another view. And as a side note, I won't address the idea yet of whether the three definitions from the classical view are, in fact, one and the same, or whether you need all three to work together as a package. I'm just trying to tease out different components of the package because I think different approaches to quantum gravity take different components of that package. They don't take the whole thing. Okay, so the second component of this package, if you will, the second possible view, is the Anderson-Friedman view. So that's everyone knows the standard distinction between absolute and dynamical object. Not easy to explain, rife with interpretive problems and details, but at least intuitively accessible to us. I think. So what's an object? Let's shove that question aside for now, but just think of fields, particles, strings, branes, I don't know. A dynamical object will be governed by the principle of reciprocity. So this is where objects both influence and are influenced by whatever other theoretical elements they may act on. And an absolute object then is anything which does act on other theoretical elements or objects without experiencing that principle, all-important principle of reciprocity. So in Anderson's words, absolute objects indicate a lack of reciprocity where they can influence the physical behavior of the system but cannot in turn be influenced by this behavior back. So background independence 2, the second type of definition, might be simply that a theory is background independent if and only if it contains no absolute objects. Again, hand-wavy, but that's the intuitive idea I want to go on with. So useful for quantum gravity here is going to be to see how theoretical elements are dynamical, that is, how are they involved reciprocally with the rest of the theory, the element of reciprocity, or instead are the elements that we're looking at as being interesting to us stipulated as initial conditions, boundary conditions, superselection rules, etc. Okay, my third and final attempt at getting a handle on classical background independence will come from Gordon Bellott's work on background independence, where he considers it to be, in short, a matter of degree. There's a short paper of his on the archive, about 7 pages, but I'd really recommend looking in terms of the details. Very, very nicely developed. A draft in 2007 that I don't think that full draft itself was ever published, but I think it's on the Phil Tsai archive. That's where I got it from. Again, I won't, because I'm trying to cover so much ground, I won't be able to do his account justice, so let me try to encapsulate it briefly. The intuitive notion he works with is that a background for him is any kind of fixed stage on which the physics of the theory is set. The stage that provides the framework that shapes the evolution of the fields of the theory without itself being shaped by them. So there's a hint of reciprocity there again, right? I'm not trying to claim that these three definitions I'm presenting are mutually exclusive. Far from that, but they might give different ingredients towards another quantum gravity interpretation of them, or use of them. The clearest cases of background independence he sees are simply theories featuring fixed fields. So those that directly determine geometry, fixed sources, or fields that have some kind of external component to them. And so he spends his whole time looking at geometry itself as being the prime suspect for a background. So what can you do about geometry? He introduces a notion of an abstract geometry. So what's an abstract geometry in his case? We can assign to each solution of a theory a space-time geometry. It's not an abstract geometry yet, but it's a space-time geometry, and then introduce a standard of sameness of geometry across solutions. I won't tease out what this is here, but he works it out in detail. And then the crucial next step is to see that any two solutions in that theory, which might be related by spatiotemporal symmetry or covariance, are assigned the same geometry, sharing the same geometry it's an equivalence relation on the space of the solutions of the theory, and we call this equivalence class an abstract geometry. So two physical possibilities correspond to the same abstract geometry if each solution of the first possibility is assigned the same geometry as each solution of the second. So his novel contribution, I think, to the understanding of background independence is this idea of degrees. So far, let me just get to the end of that slide. So far we have something that doesn't look too different from, at least in that intuitive sense, of background independence 1, where we have the idea of multiple equivalent mathematical descriptions describing the same physical reality. There's not intuitively any difference here in this, except it's teased out in a more formal way, and presumably there's a stronger standard of what similarity means between geometries. But this show what sharing the same geometry means. But what is novel about this approach is this idea of degrees. So we start with full background dependence. In full background dependence, in Gordon's view, only a single abstract geometry is realized in the theory. So that's to say that every solution corresponds to the same abstract geometry. Every physical solution corresponds to the same abstract geometry. In full background independence, you have the exact opposite of that. No two solutions, no two physical solutions correspond to the same abstract geometry. Now we have these interesting two cases. You have near background dependence. That's where the family of abstract geometries that's realized in the theory is finite dimensional. And then kind of the inverse of that, near background independence is where the family of physical possibilities corresponding to an abstract geometry is finite dimensional. So in the near background dependence, you've got a finite dimensional family of the abstract geometry, so the real physical possibilities, whereas in near background independence, there's a finite family of actual physical possibilities.
Mark, can I repeat your question?
Sure.
In what the dimension here? Is this like supposed to be a vector space?
Yeah, exactly.
Space,
yeah.
Or?
The Hilbert space, if we're going to quantum already past classical, just as like a possibility space, not spatiotemporal geometry. So sure, so vector space, sure.
Sorry, I haven't read it, I confess, but on the face of it, one could be general. One could say it's just that you need finitely many real numbers to parameterize the family in the third option. And in the fourth option, again, the family now of possibilities. Finite.
Thank you, yeah, that's a helpful way to put it. Thank you, yeah.
But you wouldn't have to have a manifold.
Yeah, no, that's right. So what's an example of these strange outliers? So something that's nearly background independent or nearly background dependent. He doesn't develop it much, but he refers us to the Carlip work, Quantum Gravity in 2+1 dimensions, as kind of being a prime candidate for something like that. So you've got a spatially compact 2+1 vacuum GR setup where every solution is dynamically constrained to be flat, but if the topology is non-trivial, there's a non-trivial finite dimensional family of classes of solutions.
Sorry, but in this case, from the geometry point of view, you only have the flat geometry. So from that point of view, you would say that you're a little bit like in cosmic space.
Exactly. You just said if it's a little bit like, that means exactly why it's nearly background dependent. Yeah.
From the point of view of geometry, because there is only one geometry and it's not really dynamical, it's not clear to me in what sense you're in a different situation than in cosmic space.
I confess I don't really understand the details here, but I think it has to do with the non-triviality of the topology.
Okay, so there's topological degrees of freedom.
That's right.
Geometric.
Yeah. Okay, so an overview now before I move into the quantum gravity domain. So as a summary, I present three different possible definitions, maybe not mutually exclusive, but some kind of start anyway, of background independence in classical field theories. The first one again is where the covariance group equals the invariance group, so call this a kind of description equivalence or gauge redundancy view. Definition 2 will be the idea that there are no extra theoretic boundary conditions, the evolution of everything, and we'll see, you know, obviously it's a very loose term, we just have to see from theory to theory what everything means. The evolution of all the theoretical elements is dynamical and reciprocal, and in 3, which we just looked at, Gordon Bellett's view, where it's just this indication that every physical solution corresponds to unique abstract geometry, so that would be background independence there, and it can occur in degrees. Okay, so can we go further than this? So I take as my motivator here Smolin's quote. That I'll just read it out. So it's true that in GR, the dimension, topology, differential structure, and signature are fixed. These can be varied from model to model, but they are arbitrary and not subject to law. I mean, he means they don't evolve. These do constitute a background. Okay, so off of this quote, I ask myself the motivating question, is it possible in certain approaches to quantum gravity to look at whatever was still, in Smolin's view, fixed here, and see if in any way it can be made background independent or dynamicized? So the rest of the talk is a attempt at trying to get a handle on that. Right. So in other more advertising type terms, you might say that to make it look interesting, you might say, could a theory or approach to quantum gravity be more background independent than GR? Okay.
So just a quick question: how do dimension and signature vary from model to model in GR?
By specification, I guess. Like, they don't evolve once you've.
You can write down GR in 15 dimensions.
Yeah.
Has a different model, but the dimension is still fixed.
It's fixed, so once you're in the 15-dimensional model, you're not going to evolve to a 4-dimensional model,
I guess
right?
I wouldn't call this a model of GR, but it's a model theory.
Well, topology, okay, then forget that you mentioned the topological structure, right? Presumably is fixed,
Sure.
right? Yeah, there we go, okay. Or signature, once you specify a signature, you're going to stay with that signature throughout, right?
Yeah, for all models.
Well, they can be varied from model to model. Okay. All right. Where am I now? Sorry. So, okay, 3 views of background independence in quantum gravity. Or actually, what it should have said is 3 approaches to quantum gravity. How are they background independent? So I should have flipped the order of views, should have flipped the order of words around, but there was a certain symmetry between the way the first sentence was presented, so I didn't break the symmetry. Okay. First I look at string theory. So because I'm trying to cover a lot of ground and respect our time limits, I won't dwell on either a setup or really any technical details, because those were covered beautifully, and both in terms of the technicalities and the concepts in the series of talks yesterday, so I simply refer you to those and references therein for further reading on this subject. So I'll just jump right to the chase. For my purposes here, in what sense are dualities, say the ADS CFT duality, in what sense is that background independent? In what exact sense, given my initial classical setup, is that background independent? So other than the Jeff's talk yesterday, which essentially answered the question for me, there is another paper, particular paper that addresses this by Moshe Rosali, where he and Jeff yesterday distinguish critically, this is a very critical distinction if you're trying to understand how string theory is background independent, between so-called dynamical backgrounds, we'll explain what that is in a second, and boundary conditions or superselection rules, superselection sectors. So Rosali says, on the topic of ADS CFT, in a gauge theory description of the system, so on the CFT side, the Lagrangian, the rank of the gauge group, and the manifold on which the non-gravitational theory propagates are all fixed for all states of the theory and for all physical processes allowed in the theory. On the other hand, the correspondence does not specify any background metric, background values for any of the fields, or any other aspect of the theory that can change dynamically. When specifying the boundary conditions, the gauge theory description already sums, that's the key there, already sums the contribution of all bulk geometries and other field configurations, which satisfy the boundary conditions. None of those backgrounds makes an appearance in the gauge theory description. In that sense, because it's a gauge theory, the description is as background independent as GR. So that's, in my opinion, a very clear use of background independence in that first view, the gauge redundancy view. Right? So recall there's two types of diffeomorphisms here that are relevant. Those which do change boundary conditions. Those are global symmetries and they do have physical consequences, so we don't want to go there if we're talking about background independence. But we can talk about these, the bulk diffeomorphisms. So in that sense, they are redundancy of the description, have no physical consequence, so dualities are background independent in that sense. But there's some more conjectures I want to throw on the table. It's just a review of what I said. So the bulk diffeomorphism gives a sense of gauge redundancy, and therefore background independence there. But very interestingly, and so I'm really glad I went after everybody, depending on how the understanding of fundamentality of the dualities turns out, that's from Eleanor's paper in this seminar, I think there genuinely could be a further sense that dual descriptions contribute a sense of background independence. In the sense that, again, depending on how the way that debate turns on the fundamentality question. So is one side of the description, or one dual rather, more fundamental than the other? Is that an ill-posed question? They're just fundamental, period. There's a sense in which forgetting the individual theoretical elements of one of the duals, like the fact that the CFT is a gauge theory, therefore background independent, there's a higher order or higher level of background independence there because two dual theories are both or themselves fundamental. It's not as if one is more fundamental than the other. So maybe that's a novel kind of background independence. Just want to point out then before we move on that in the duality understanding, boundary conditions and superselection rules still play an important role. So in taking kind of that Smolin attempt, or that Smolin call to action further, could there be a theory of quantum gravity or an approach to quantum gravity in which boundary conditions, loosely geometry itself evolves? What would that look like? Okay, so we move on to loop quantum gravity now. And again, similarly as in the string theory side of the talk, I refer you to the wonderful work done yesterday by the other participants in the seminar who spoke out to loop quantum gravity. And so I just want to answer the question here, or try to get a handle on the question, in what sense are some of the key theoretical elements, namely the spin networks, which are the basic kinematical objects, and spin foams, which are the basic dynamical objects of the theory, background independent. Recall that spin networks represent particular embeddings of the kinematical state of the gravitational field into a 3-space. And then S naughts are equivalence classes of spin networks under diffeomorphisms. So it's a no-brainer that that's definitely background independent in sense 1. It's a kind of description redundancy, right? Gauge redundancy, if you will. Spin foams, similarly, I mean, the operation will work differently, but we'll get the same answer. Recall, okay, so spin foams are dynamical processes, so they're analogs to Feynman diagrams or path integrals. They're responsible for the dynamical evolution of spin networks. In particular, for our kind of looking at things in the lens of background independence, They describe coarse grainings of spin network histories, or, I really love this term, sum overall histories, in order to describe the dynamical evolution. So in this sense, the dynamics of spin foams clearly shows that loop quantum gravity is background independent theory in the sense of, again, one, there's no reference to any particular history, rather a sum overall histories in a spirit similar to gauge equivalency. So what's the prognosis so far? Both string theory and loop quantum gravity can be characterized as background independent insofar as the dynamics are characterized by analogs to gauge redundancy or equivalent descriptions, but there still are individual histories, matrices, descriptions, etc., that loosely are taken to be a mathematical equivalence class of the same physical reality. So again, in very hand-wavy here, because I'm trying to get at the core concepts, they're both background independence in the sense of it doesn't really matter which description, strand, path, history one chooses. Very hand-wavy, but I like that because it gets at the concept. So, are there approaches to quantum gravity where one can trace dynamical evolution, the evolution of the geometry, the boundary conditions themselves, through a single mathematical description of the dynamics, rather than equivalence classes, embeddings of abstract graphs, etc., into manifolds? If this were achievable, it would seem to be background independent in a specifically different way than the other theories. So more like a definition 3, like where the attempt is made to dynamicize, if that's a word, all the theoretical elements of the theory. So I'll talk about geometrogenesis here. Daniela already spoke about that on the Friday talk, and this is a family of approaches to, it's like a subset of a subset, right? It's a family of approaches within themselves, condensed matter approaches to quantum gravity, where the lattice structures themselves are dynamical. And I'm only going to talk about one such approach within that already subfamily, which is quantum graphity. So again, it's a type of geometrogenesis. The geometrogenesis, for my purposes here, very simply means that there's a goal to construct a quantum theory of gravity by analogy to condensed matter phase transition, like the icing model of magnetism, where the genesis part is obviously here. That's your phase transition, so geometry is born. So a brief overview of the kind of history or components of quantum graphity. The models tend to have both emergent matter and emergent geometry. So this is what creates geometry and gravity. The emergent matter component of the theory comes from a seminal paper by Levin and Wen, which I'll talk about very briefly later. How much time do I have? Maybe it would be super brief. When did I start?
5 minutes or so.
Oh, okay, I'll have to speed. Sure, thanks. Thank you. The main original work was done by Fotini and Lee and many collaborators. So what I will reference to very quickly, since I see I'm almost out of time, is 2 papers or 2 uses of this approach. One is in the construction of a Bose-Hubbard toy model of evolution of geometry, and also the very recent development published a few months ago by Chen and Plotkin for the emergence of spacetime manifolds using this approach. So time is short, so I'll leave this to the slides posted on the net. Graph theory preliminaries. I think everyone in the room would be very familiar with this. What the kind of basic structure of the graph is, of a graph is. In their case here, as in many graph approaches, lattice approaches to quantum gravity, you've got the main kind of distinction in the approach is the difference between what an edge and a node or a vertex is. So every edge can be either in a ground state or off, or in one of several excited states. So here's the Hamiltonian for, Hilbert space for if you had to spin one system here for the 3 states, or for the 3 edges rather, sorry. I'll leave this slide for review later. It's just give you the basic tools you would need as a philosopher to understand the graph theory approach. talks about the core concepts: embedding, eccentricity, paths, lengths of paths, what a diameter of graph is, etc. So that's background. That's kind of background review. So how does geometrogenesis work? So there's a coupling of the approach of using a graph with the emergence of matter degrees of freedom from the Levin and Wen paper, where they propose a mechanism called string net condensation. Rotors, which are rotors, or quantum degrees of freedom on the links of a cubic lattice. In certain regimes, the rotors organize themselves into what appear to be effective extended objects, so they call them string nets. And since it has two types of excitation, the ground state of the string net, the collective motions of string nets give rise to effective photons and effective charges. So it's like a U1 gauge theory. So putting this all together, you're able to get lattice and matter degrees of freedom, where the lattice interacts with the matter. Matter tells geometry how to curve, and geometry tells matter where to go, very kind of intuitively speaking. So the quantum gravity approach attempts to define geometry via the dynamics of matter. So I'll just read the last quote there because I'm running out of time. The emergence of locality from the dynamics of a quantum many-body system is as follows. No notion of space is presupposed. Extension, separateness, distance, and all the spatial notions are emergent from a more fundamental notion of interaction. So the interaction is kind of the key dynamical notion there. The locality of interactions is a consequence of the approach and not a principle. So they promote the interaction terms between two systems to a quantum degree of freedom so that the structure of interactions itself becomes a dynamical variable. This makes possible entanglement between matter and geometry. So visually, that's how Hamiltonian would act on edges in various ways. Here are the main, kind of, if this were a soup, here would be the main ingredients you'd put in your chicken stock, your salt, your vegetables, and so on. You start off with defining a Hamiltonian before you quantize anything, where you represent both interacting and non-interacting edges. Build up a Hilbert space. We've got a base state in that Hilbert space, which again is entanglement between the quote-unquote matter degrees of freedom and the quote-unquote spatial degrees of freedom. And your final Hamiltonian, which is key for understanding the evolution, is given as a sum of all the contributions of the exchanges of energy in the system. So links can pass along energy. I forget what the sub V is. X is exchange of energy, and hop is where, really it's an analog of movement. So say a photon moving from edge to edge to edge, hopping. So again, the key is a phase transition. So you'd have a very high dimensional graph representing the cosmological origin, right, of the universe, so high entropy state, and then this energy contained in the high entropy state is, using the Hamiltonian from before, slowly spread out until phase transition happens, so you reach a low entropy state with low dimension, large diameter. At early times, the graph is in a very disordered state, and the average valence on each node is large. As the system cools, so that's your phase transition, some of the degrees of freedom become frozen. So that's exactly the motivation there for the thinking about the emergence of classical spacetime. Other kind of cosmological features or classical features that try to be reproduced using these models are toy black holes. So I'll give you a reference there. So a region where, it's kind of a sub-region of the full lattice, which has fairly low dimensionality here, but then there's high connectivity in a certain zone, so it's like a black hole, toy black hole. And then the last kind of bit is the most recent work about emergent manifolds using this approach. I'll just read some of this out. A manifold can be approximated by triangulation, which in turn can be viewed as a graph with simplices. From this observation, one can consider how a graph may give rise to a manifold from a family of graphs, following some constraints and obeying some set of rules for dynamical processes. Is it possible that a manifold-like structure can emerge? To be more precise, consider the possibility that a graph G gives rise to a smooth manifold M. A vertex in G corresponds to a point in M, where a pair of vertices in G are connected by an edge. The corresponding pair of points in M have a certain distance eta. And so on and so on. In such cases, one can say that the manifold M, including, this is the key for me, including its dimensionality, topology, and metric, emerges from the graph g in the continuous limit. So practically, of course, this is not solved analytically. It's run through Monte Carlo simulations. So there's some very pretty pictures of the dynamical evolution of the graph. So here you have your Big Bang, if you will, the start of the system, high entropy, and slow cooling. So they started the system, I believe it's with 200 nodes, or sorry, 200 vertices, right? And they study the topological properties of the emergent structure, the emergent manifold. So, to finish off, what's background independent in here? So in a trivial sense, there's a permutation invariance of the lattice model as any kind of lattice approach would be, right? I don't think that that's any different from the kind of diffeomorphism invariance of background independence that we've been talking about that many other approaches share. But, this is my speculation, but there seems to be a more special or an additional kind of background independence at work here, namely the dynamical evolution of the model itself. So where underlying features, what we would normally take to be underlying geometrical features like, underlying background features like topology and dimensionality are emergent. So it's more like that, kind of, if you will, in a wishful way, the ultimate fulfilling of the Andersonian project of dynamicizing all the elements of your theory. This is just my understanding of how permutability of the graph is the same as diffeomorphism invariance. Let's skip over that. Basically, I've said that. I know I'm out of time. So, right, you're supposed to end where you began. So, I just show this split again of the two. Not that I'm talking about the contents of the book, just their titles are what interest me. So, whether you've got the end of time or time reborn. In an approach where the background independence is exclusively kind of the diffeomorphism invariant equivalent mathematical description type, you'll have probably more like something the end of time. Whereas in a geometrogenesis approach where you have a dynamical evolution of the very kind of boundary conditions of your model, you have time as actually really the only thing that's real and driving everything on. So that's it. Thanks.
Mark. So I think time is about to end. Maybe we could just have a couple of questions so we don't get too far behind. Brian?
Something that's a little confusing for me. You mentioned the Giulini paper. I believe this is the one I have in mind, but a little before that, Robert Garrosh pointed out that in general relativity, the volume element actually counts as because it's the same in all models, neighborhood by neighborhood. It would seem to count as an Andersonian absolute object even in general relativity. So if it's not really obvious what background independence or substantive general covariance or whatever should mean, and still have general relativity satisfy it, what impact does that have on the desirability of general covariance? If your alleged paradigm case actually is not an example, or may not be an example.
Yeah, so I'm not so that's that part where I say I would need a whole other talk to talk about the motivation of it. I was just doing the teasing out here. I think that it's not necessary that our kind of core held up theory like GRB, in fact, background independent, as long as certain elements of the background independence move or program were implemented there, even if, as you say, I appreciate that. I didn't know about the volume element stuff. I'll have to look that up. Incorporate that. Thank you. You know, in the final analysis showed GR to fail as a background independent theory. I mean,
so it could still be seen as a progress towards the desired.
Sure. Thanks for that. Yeah.
Bianca, I think I saw your hand next to you.
Yeah, so I'm not sure I completely agree with the division you make between like the spin network and spin folding version being mostly background independent in terms of gauge equivalence, because once you have 2 points, like one might be really gauge equivalence, the other point was you sum over everything. So summing over everything means that you sum over, sometimes you sum over gauge inequivalent gauge equivalent things. Usually you try to avoid it, but the point is to sum over gauge inequivalent things. statistical physics kind of arguments, and they just introduce kind of the background time as a convenience. So I'm not sure I would completely follow your division and say
Okay, thank you. That's helpful. Thank you.
these are completely...
That's why I came here to learn. Thank you. Okay, thanks.
So just to remark more on this point, so the idea of geometrogenesis is the fact that there is a phase that is geometric and possibly other phases which are not, and you reach it through a phase transition. In itself, it doesn't distinguish a model from another. In fact, when I mention it in my talk, I mention it in the context of a field theory formulation of the quantum gravity streamfolds. And in fact, as Bianca was remarking, there are the graph structures, or the complex structures in space-time, the folds, are dynamical, exactly as they are dynamical in the quantum gravity. And actually, one can argue that the quantum gravity model is as dynamical as the others in this sense, but it's less dynamical because it works, less background independent because it works with a given and preferred notion of time. So I'm not sure in what sense when you introduce an additional background time variable that would make your theory more background independent. In these other modes, you have the same dynamical graph structures without even using the notion of time to describe their dynamics.
Yeah, so that's very helpful. I hope to talk to you more about that. My quick follow-up question to that then is, or question on a question, would be, what is it that evolves in what you were saying in the spin foam? What is that evolves? Is it individual histories that evolved and we sum over all of them, or?
So the statement would be applied to the formal path interval for gravity. To define the amplitudes for a certain possible history, you sum over all histories weighted by that amplitude, and that gives you, depending on how exactly you define the amplitude, something that looks like different two-point functions for the boundary geometries.
Yeah, see, it's that possible histories which really interests me. I mean, I may be understanding the physics of the gravity completely wrong, of course. I thought, though, that it doesn't incorporate the idea, or does not in any way build on the idea of the possible history, but there is just one evolution, one history, which may be its downfall. Yeah, that's exactly a preferred notion of time, but there is no right?
It has not been done because what they try to do is different, but you can reformulate quantum gravity as a sum of the histories, except that they will have a preferred foliation with respect to the background time. But it's a quantum mechanical theory.
Okay, so it's just a matter of the
so you can write
formulation.
Some of the histories, but just with a preferred slicing in terms of rust, because there is a preferred time variable. But it's not that, as a quantum mechanical theory, you can write it canonically.
Right.
Shouldn't really matter.
Well, why don't we thank Mark again, and